told a high-tech company purchases a new computing system, which has an initial value of V. We're told the system depreciates at a rate F equals F of t as a function of time t, and will accumulate maintenance costs at the rate G equals G of t, where t is the time measured in months. We're told the company wants to determine the optimal time to replace the system. So that's the point of this exercise, is to find this optimal time. In part A, we are given the function c of t, which is defined to be 1 over t times the integral from 0 to t of f of s plus g of s ds. We're asked to show that the critical numbers of this expression c occur at the numbers t, where c of t equals f of t plus g of t. Well, to find the critical numbers, first we need to find the derivative c prime of t. We'll do this by using the product rule. So c prime of t, this is the derivative of 1 over t, which is negative 1 over t squared times the integral from 0 to t of f of s plus g of s ds, plus 1 over t times, and then using the fundamental theorem of calculus, we take the derivative of this integral. And by the first part of the fundamental theorem of calculus, this is 1 over t times, and this is just f of t plus g of t. Now, to find the critical numbers, we want to find when c prime equals 0. So, if c prime of t equals 0, well, then it follows, after rearranging this expression, that 1 over t squared times the integral from 0 to t of f of s plus g of s ds equals 1 over t times f of t plus g of t. And we can multiply both sides by t, and we get that 1 over t times the integral from 0 to t of f of s plus g of s ds equals f of t plus g of t. Notice that this left-hand expression is the same thing as c of t, and so we get that c of t equals f of t plus g of t. And this expression is true. This tells us that c of t equals f of t plus g of t when t is a critical number of c. Then in part B, we're given another expression, well, our rate of depreciation f of t. So we're told that f of t is equal to v over 15 minus v over 450 times t for t greater than 0, less than or equal to 30, and is equal to 0 for all t greater than 30. And we're told that the maintenance costs rate, g of t, is v times t squared over 12,900 for t greater than 0. we're asked to determine the length of time big T for the total depreciation d of t. The total depreciation d of t, which is the same as the integral from 0 to t of the rate of depreciation f of s ds. We're asked to find the length of time big T so that the total depreciation equals the initial value of the system V. So first, let's put the first piece of our function f of s into our total depreciation. So we have our total depreciation d of t is equal to the integral from 0 to t of v over 15 minus v over 450 times s ds. And now we'll integrate. So we get that d of t is equal to v squared, v over 15 times t minus v over 900 times t squared. And now we want to solve the equation d of t equals v. So d of big T is going to be equal to our initial value v. Well, this means that v over 15 times big T minus v over 900 times big T squared equals v. And so we obtain this quadratic equation, which we can solve. It actually reduces to a simpler form. Multiply through by 900 over v, and you should get 900 equals 60 t minus big T squared, which we can factor as t minus 30 squared equals 0. And therefore, big T equals 30. And recall that the unit is in months. And so this is the length of time for the total depreciation to equal the initial value. Then in part C, we're asked to determine the absolute minimum of the expression C on the interval from 0 to big T. To find the absolute minimum on this interval, let's plug in the expressions f and g into the expression c of t. So recall what c of t was defined to be. Which is 1 over t times the integral from 0 to t of f of t, which for t less than 30, less than or equal to 30, I should say, this is v over 15 minus v over 450. S, and then g is plus vs squared over 12,900. ds. And now we'll integrate to obtain the polynomial form of c. So this is equal to 1 over t times v over 15 t minus v over 900 t squared plus v over 38,700 times t cubed. And this simplifies to v over 15 minus v over 900 t plus v over 38,700 times t squared. Now, we already saw in part A that c has critical numbers when c of t is equal to f of t plus g of t. So, to find the absolute minimum, this is going to be at a critical number on this interval. And so we have our left-hand side, which was c of t. This now becomes f of t plus g of t. And the right-hand side is the same, v over 15 minus v over 900 t plus v over 38,700 t squared. And now we can plug in the expressions for f and g again. So we get v over 15 minus v over 450 t plus v t squared over 12,900 equals v over 15 minus v over 900 t plus v over 38,700 t cubed. Sorry, that's t squared. And so we end up with a quadratic expression. And if you want to, you can simplify this. This should factor eventually as t times 2t minus 43 equals 0. And so it follows that our critical numbers are either t equals 0 or t equals 43 halves. Now, because we're only looking at critical numbers in the interval left parentheses 0, right bracket t, we're only considering t equals 43 halves. Now, to determine if this is in fact the location of the absolute minimum of c, we'll test the critical numbers and the endpoints of the interval. So we have 0, which is both an endpoint and kind of a critical number here. If you plug it into c, we simply get, using our expression above for c, v over 15. On the other hand, plugging in 43 halves, c of 43 halves is v over 15 minus v over 900 times 43 halves plus v over 38,700 times 43 halves squared. And this is all an expression in v, which you can simplify. The first expression was approximately 0.0667 v. And the second expression, c of 43 halves, is approximately 0.0547 times v, which is slightly less. And finally, we test the right endpoint. So big T could be anything from as small as, well, 0, I guess, up to 30. We do have T. That was 30, right? So C of 30, plugging this in, this is V over 15 minus V over 900 times 30 plus V over 38,700 times 30 squared. And this is approximately 0.0566 V. Which is slightly greater than C of 43 halves. Therefore, we see the lowest of these, C of 43 halves, which we saw was approximately 0.0547 times V, is the absolute minimum. On the interval from 0 to big T. Okay, so in other words, this is the optimal time to replace the system at 43 halves months, because this is when the value of C will be the least. Okay. Finally, in part D, we're asked to sketch the graphs of C and F plus G in the same coordinate system and verify the result from part A. Recall part A was about the critical numbers of C. So we've already found the expressions for C and F plus G in previous exercises. So I'm just going to sketch the graphs very quickly here. The x-axis will range from 0 to 30, the y-axis from 0 to about 10. Well, I should really say t, since the variable is t. The t-axis and y-axis. So I'll graph C of t in red. It starts in the y-axis at the point 0, v over 15. So technically, we weren't told exactly what v is. But if just for the sake of argument, we say that v equals 100, then it makes it easier to graph these. So v over 15 in that case would be a little bit less than 7. And it's going to decrease to the point 21.5, and then if you plug in 100, to the expression for the absolute minimum. It's about 5.4722. And so that's an absolute minimum. So we decrease smoothly until we reach that point, and then we start increasing again like this. And so this is C of t. Then I'll also draw f plus g in blue. This also has a y-intercept of 0, v over 15. And it also passes through the point 21.5, 5.4722. Since we know that 21.5 is a critical number, well, just by graphing, we know this is true. But on the other hand, f plus g has a minimum much sooner than that. And so it looks more like this. Oops. And this is f plus g. And so we see that the absolute minimum of C occurs at t equals 21.5, which is, of course, where it intersects with f plus g. And so this confirms part A.